Hey, everybody. I'm really thankful that more and more people are joining us. I want to do a quick introduction of our speaker. Dr. Tristan Behrens is an AI expert, a composer, and educator. He has an extensive track record in successful DO projects. His focus is deep neural networks. He has published several albums of music composed with a computer, music that is actually enjoyable and nice to listen to also. And yes, he also has his own company, AI Guru, where he does yes, prototyping and so on. And yes, so computational linguistics on its own is a really interesting subject and kind of a niche subject in the broader area of computer science. But when you combine it with music composition by using NLP models, it gets even more fascinating, I think. So I think it's going to be a really interesting talk. So thank you for joining us.
Thank you very much for the kind invitation. I'm very happy to be here today. And yeah, you are absolutely right. I mean, there are so many use cases in AI, but if I have to choose between optimizing a process and creating an AI that helps me being productive and creative, I would tend to go down the creative road. There's so many things you can do. So today I will bridge the gap between natural language processing and music generation, and I'll tell you it's just the same. It's just the same. It's just a matter of data set. What you see here right now is Johann Sebastian Bach, imagined by one of those many generative AIs that are currently available. I think this is Midjourney. It's comparable to DALL-E 2. You prompt it, you say, well, this is please generate Johann Sebastian Bach in the cyberpunk style, and just goes ahead and generates something. I think it's a diffusion model. So today, composing with AI. Let's go straight to business. Johann Sebastian Bach. Gentle reminder, Erinnerung, I love this word. I had an old professor of mine when I studied computer science, and he always had these anecdotes about historical events and biographies of famous mathematicians. And every time he said something about this Erinnerung, they dropped the pens because not relevant for the exams. So Johann Sebastian Bach was born in 1685 and he died in 1750 in Leipzig. And we all know him for being a musician, composer, and a self-learner. Self-learner, I think, quite important. Even back in those days, I mean, today being a self-learner, I think is quite easy. Back then, well, he always had to go travel around and then find sources of knowledge that he could where he could learn from. And musically, he was active in the late Baroque era, from 1680 to 1750. And good thing is, although comparable to today, this is more like information dark age, where not so much information survived in comparison to today. Still a lot of things survived, including his Bach-Werke-Verzeichnis, which has a little bit more than 1,000 pieces of music that are available. Here is a piece of Johann Sebastian Bach music. It's a chorale. And for those people who don't know anything about music production, this is a view called piano roll. Maybe you have seen these old westerns, or I think it was even in this series Westworld, where you have a piano playing, and it plays from a piece of paper with holes in it. This is a so-called piano roll. And if you turn it around, you can actually read the music. So from left to right, there's time. From bottom to top is pitches, so different notes on the piano. And this is what you see when you work with Fruity Loops, when you work with Cubase, with GarageBand, with Logic, with Ableton. It's just a nice notation for music. So an idea of composer would be to just click. So what you see here, quite a lot of note events. There is some structure in it. This is a so-called chorale. A chorale is a piece of music that is situated in churches. So usually a chorale would be sung in churches. So the musical instrument would be the human voice. It's not the organ, it's not piano or any strings or anything else that was available back then. It was intended to be sung. And here, SATB, soprano, alto, tenor, and bass, you have 4 voices. So usually soprano and alto are female voices, where soprano is a high female voice and alto a lower female voice. The same with tenor and bass. Bass is a very low singer and tenor is higher than the bass. So the idea is you have a choir singing and you have those 4 voices represented, and each voice sings something. What Johann Sebastian Bach has done here, it's based on spiritual melodies. So already back in that time, there were a couple of melodies available, but the trouble with those melodies, only one voice, not four voices. So Johann Sebastian Bach went through the motions and took roughly 400 of those melodies and added the 3 missing voices. We'll make it complete SATB picture. And for us, we are very happy about that because, well, data science and deep learning, you always want to have a data set. Roughly 400 of those chorales have survived and are currently available. And why am I talking about this? Well, long story short, those chorales by Johann Sebastian Bach can be considered the hello world for music generation. So this is where everyone starts. 400 chorales is not that much. It's something that you can process. It's something that you can train. It's definitely not the biggest data set because, well, 400 songs, almost nothing. But in order to learn how to do that exercise, in order to create a neural network and train it, to learn how this is done, and then turn it into something that you can compose with, very, very good start. And after that, the only thing that you have to do is scale. You take bigger data sets and bigger and bigger and bigger data sets. And also you would think about using bigger and bigger models, but still the same architecture. Speaking of which, transformer language models. This is something I think all NLP people, we like that. So what you see here on the right side is a transformer called the transformer. It's actually the first transformer that we saw in the publications in 2017. This transformer, very interesting, the use case is translation. So machine translation, taking a sentence in one human language and then translating it to a second human language. So what you see here is on the left side of this graph, you have the inputs, which would be some representation of a text in one language. And we immediately think about tokens. So a token representation of a text. So it's not spoken language, it's written language. And also there are the input embeddings where we all know, well, those are word embeddings, those are word vectors that you can do math with. On the right side, on the other hand, also fairly interesting, that's the output. This is a part of a neural network that, based on the input, generates the output, which in this case is the translation of a text. And the beauty about this is that this picture is rather complete. If you would just take the left side of this diagram with the inputs, this is called an encoder-only transformer. And in this family are models like, for example, BERT and Roberta and all these from the Sesame Street. And I think NLP Munich has this Sesame Street-like logo, and I think you're all aware of that. The right side, on the other hand, is decoder-only models. Those are the models that I like most. They can be used for text generation. So GPT, GPT-2, GPT-3 is one of those. And if I'm not wrong, DALL-E for image generation is also this one. Not DALL-E 2, I think it's just DALL-E 1, but it's also an encoder-only transformer. Transformers have been state-of-the-art in NLP for quite some time now, quite some time, 4 or 5 years. And what we know, well, they work with texts. That's where they come from. And we learned recently that they can also be applied to source code. And here, well, GPT-3 was trained on quite a lot of data, like 50 gigabytes and later, I think 500 gigabytes of text data scraped from the internet, cleaned to a certain degree, but it still included source code. So people were surprised that this general GPT-3 could generate some source code. Source code was not convincing, so they fine-tuned it on, I think, the entire GitHub. And now there's a product called Copilot, which I love, which is available, and you can use it for programming. So you have a deep neural network that helps you programming, and I love this a lot. I mean, as a veteran programmer, I started programming in the 90s, you always have this pair programming scenario. It's quite amazing, and it's increased productivity. Can also be applied to images. The only thing that you have to make sure is that the inputs and the outputs have a certain representation. The architecture beyond that would still be the same. It would be a transformer. Can also be applied to sound. I mean, sound classification is one thing to do. Also, sound representing music, jukebox by, I think, OpenAI is available. And finally, that's why we're here today, it can be applied to music. So if you find a way to take a piece of music or a data set of pieces of music and map them to something that you can put into the, for example, the right side of this picture, then you would have a mapping from music to NLP, and then you can just go wild. So if you effectively reduce your music generation problem to text generation, then everything is fine. And speaking of which, this is the principle that we need all of the time when it comes to generating autoregression. It's all about predicting the next token. So you have a piece of text. What is the next word? What is the next token? And you can easily imagine that in order to train a neural network on that, you just need a lot of data, a lot of text. And then you would take a piece of text, maybe a couple of words, maybe an entire paragraph as an input, and the output would be the missing word. And this translates to self-supervised learning, where you don't have to aggregate, find the labels yourself. You just write some source code that from dataset gets the labels. Here's an example. Harry Potter is the great, and if you like, maybe you can do some auto-completion of that. What would be the next token?
Wizard.
Wizard. What else? What else is he great? I got a few examples here. So wizard, of course, because, well, maybe you all read Harry Potter, the entire series, plus all the additional material, and you know that he's a magician, he's a wizard. He's also a hero. I mean, the whole 7 books are about his hero's journey, and I think he's in Gryffindor. And this tells you the whole story. And that's the only principle that you need to remember when it comes to generating anything. That you have something and just generate the next thing. What you can also imagine is that you can repeat this in a loop. So Harry Potter is a great. Wizard would be the next token, and maybe the next tokens, if you do it a couple of times, wizard who was a student at Hogwarts School of Witchcraft and Wizardry. So if you do it a couple of times, you could even generate entire sentences, entire books out of that. And if my memory serves me well, the large language models like GPT-3, they have a sequence length of 2048 tokens, which is quite a lot. And I remember that I used those language models to generate Harry Potter-like stories. So generating a chapter is quite good. And I think with the free account of OpenAI's GPT-3, you can do 2, 3, or 4 chapters, and then they ask you for money. But this, again, you have to keep in mind. Predicting the next token is all that they actually need. It's hilariously effective when it comes to generating things. So now the big question. I got a piece of I got an image for you. How to bridge the gap between music, where you saw, well, here this is some representation of some notes where you have note length, when the note starts, when it ends, what's the pitch inside the scale. And on the other hand side, you would like to have something that at least looks like a text, where you would have a sequence of tokens. And here we are all standing on the shoulders of giants, especially including me. I found this great paper, was sent to me by a dear friend called MMM, Exploring Conditional Multitrack Music Generation with a Transformer, released in 2020, and it's just a great paper to read. What is so great about this paper is that it caught me by surprise, because usually when I read papers about deep learning, I have a look at, well, what's the data set, and then what's the model architecture, and then the pictures and evaluation and so on and so forth. This paper, on the other hand side, is almost entirely about data, and especially the data representation. And when it comes to deep neural network training, there's one paragraph and says that, well, for training we used the GPT-2 implementation by Hugging Face, and we used 6 layers and 8 attention heads. Embedding size was 512, and the sequence length 2048. That's all. That's all. No picture, no new architecture. They just said you go to Hugging Face, you use their implementation of GPT-2, and then you train. So Basically, the most work you would be doing would be representing music as a sequence of tokens. And here, to explain this picture, you see bar, track, and multi-track. The idea behind that is that music is hierarchical. When you listen to some music on the radio, when you listen to your CDs or vinyls or on Spotify, when you create your music, usually it comes in tracks. So you have a drum track, you have a guitar track, you have a bass track, maybe some synthesizer, you also have a vocal track. So it's multi-track in nature. What we see here on the right side under multi-track is you have a piece start. This is a word, a token, indicating that here is a piece of music about to start. You always need that because you cannot create anything from emptiness. So if you want to generate some music, you have to start with piece start. That's why it's always there. And then you see this pattern repeating: track start, track end, track start, track end, track start, track end. So depending on what kind of music you have, depending on the number of tracks you have, you would have multiple track start, track end, track start, track end, and so on and so forth. And inside this is the hierarchical nature. You have the actual track representation. What is a track in your piece of music? What is the guitar? What is the drums doing there? And we see here in the middle, track, just a pass between track start and track end. It has a couple of tokens that are very, very interesting. The first token, inst 30. Maybe this is a guitar, I can't remember. There is a standard for instruments called General MIDI, and it has 128 numbers, and each number representing a specific instrument, like different guitars that you have, like different synthesizers, elements of an orchestra, ethnic instruments, effects, and so on and so forth. So it's a standard that is encoded. And in the data sets, you usually have an annotation that tells you this is a piano, this is a harpsichord, this is a guitar. So it says instrument number 30. And then there's the density. And the density is how many notes you have in the track. So higher density means more notes, smaller density means less notes. So it's something that you can use to control. So you could ask a neural network to generate instrument 40 with density 5. You could also change the numbers in there to get something else. If we continue here in the middle, you see bar start and bar end, bar start, bar end, bar start and bar end. This is also another nature of the music that, well, most of the time it comes in bars. You know, there's 4 on the floor, 1, 2, 3, 4, 1, 2, 3, 4, and so on and so forth when you go to the club on the weekend. That's usually a bar with 4 beats. And if you're dancing a waltz, then it's 3, 4, 3 over 4, dum 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 dum. And this is represented here. So you have a track, and a track consists of bars. And then on the left side, this is where the actual music lives. Multi-track and track are more about structure of a piece of music, and the bar is the actual music itself. So you have note on, time delta, note off. Means that it starts note number 60, pitch number 60, maybe it's a C, I don't know. So a note starts, and then there's a time delta, which might be 2 16 notes, so maybe an 8th note, and then the note ends. And then you see note on 64, this is another note starting, and here, very surprising, note 67, also starting at the same time, so you're doing a chord here, and then time delta passes 4, and then one note ends, and then more time delta, and then another note ends. So this is an encoding, like a description of how to encode your music into something that gives you, first and foremost, multiple tracks. Each track has an instrument and a couple of bars, and each bar has note on, time delta, note off events. So there's the actual music happening there. Here's an example. It's another Bach chorale. You see 1, 2, 3, 4 voices. So the red one would be the bass, and the greenish, bluish thing would be the soprano, and then everything in between. It's 8 seconds long. I think is 120 beats per minute. So every 2 seconds is 1 bar. 1, 2, 3, 4 bars we see here. 4 voices singing together. So now the question is, this is definitely something that an AI would not directly work with. How would it look like as a text? Lo and behold, here's the text. This is just the implementation of the picture we've seen before. So there's P start, there's track start, instrument here, it's the bass, and then you have bar start, note on, time delta, note off, and so on and so forth. So the entire text that you see here in dark red and in red is the bass voice of that piece of a chorale. You can easily imagine, and I put it here at the end with the dots. After that track, you could have another track, and another track, and another track, until you have all the 4 tracks in the music. So again, the only thing that you have to do is you find some music. You can find it on the internet. Usually it comes as MIDI files, fairly easy to use, fairly easy to load. There are Python modules available. And then, well, you just, quote unquote, have to map those MIDI files to that kind of representation, where you have P start and you have the track start and you have the instrument and the bar start and the notes and bar end, track end, and so on and so forth. So it's just one linear sequence as a music representation. If you have a neural network trained on that does token-wise generation, you could just start with P start, and I think I'll show you that in a moment, and it would generate more and more and more and more and more based on what you started with. With P start, it would just generate anything from scratch. If you would provide a P start, track start, bar start, and a couple of note events, it would continue with that piece of music. So you could both use this AI for creating something entirely new from scratch, or you could provide some music. Maybe you have a nice bass line and you would love to have the drums or the guitar accompanying that. So you would feed in the data that you already have and let the neural network generate that. And if you think about this, that's the same thing that you would do in text generation with GPT-2 and GPT-3 and all those others that are now available, where you would start with a piece of text, that's the prompt, the conditioning, and you would allow the neural network, the transformer, to continue the text that you have provided. Sometimes it creates something nice, then you keep it. Sometimes it doesn't create something nice, then you would remove it. And then after a couple of minutes, or well, maybe a little longer, you have maybe a good text that you can publish. And if the text is a music representation, you might end up with a good piece of music. So now would be your chance on your devices, because well, we have a little trouble with me sending audio to you. If you like, please go to ki-musik.de. There's a link that I provided you, and I show you here, ki-musik.de. When you go there, you find a couple of things. Well, kind invitation. If you like to connect, I'm on LinkedIn and I am on Twitter, so don't hesitate, just send a connection request or follow. Would be very, very happy. And here are a couple of things that are fairly interesting. Let's start with that one, dataset. Hugging Face. I love Hugging Face. Unfortunately, I still have to wash my t-shirt. I'm very proud that I got one of their t-shirts. And this is a dataset that is available on Hugging Face datasets. And this was generated using the JS Fakes Chorales dataset by Omar Peracha. This is a dataset that has 500 Johann Sebastian Bach-like chorales. So it's a little bit bigger dataset, and it was available in MIDI, and I really like Omar, so I said, well, okay, can I please use your dataset and then pre-process it into text and then put it in Hugging Face? And he said, oh, no problem, they will go ahead. So I took all the MIDI files, I pre-processed them, and here you see a couple of examples. So this is an entire piece of music, the blue thing here. And nothing now to be surprised and scared of. P start, note on, bar start, it's the whole thing. So you have a data set that you could already start with, already pre-processed, so you don't have to go through the motions and find MIDI files and then write a mapper that would yield these samples already there. If you would like to do some training, getting started, if you'd like to learn that, well, this is where you could start. And there's another thing here, JS Fakes bars. No, there's a data set.
Is it okay if I just interrupt for a question while we're on the topic, or would you like to answer after we're just completely done?
Let's ask and let's discuss afterwards.
Okay. Let's just.
Perfect. So So keep tight to your questions. We will answer all of them. Okay, here. On the other hand side is one neural network that I have trained on some music on the same data set. And here I used GPT-2, just straight to business, couple of lines of code. And if I run this, still has to load the model. You start with pstart. And then after the model is loaded, it would generate a couple of tokens until some ending condition is met. Sometimes you stop the generation when you have reached a certain token. Sometimes you stop the generation if you have a certain amount of tokens. So you see it here, pstart, and it generated all of that. This does not help us yet. That's why I've hidden somewhere here a Jupyter notebook that would take the generated text and make it audible. So it maps it to MIDI files, and then you can listen to the MIDI files. So it's quite straightforward. So there's a music model available on Hugging Face Hub, and there's also the dataset available. Before I continue, let's change my mind slightly. I want to talk about a biblical story. Personally, I am an atheist. I dropped out of church in the 1990s, but still, we still celebrate Easter and Pentecost and Christmas. So this is a biblical story that happened between Easter and Pentecost last year, so 50 days. Before that, I was in a kind of startup situation where I was working on AI music, and then the project ended and I was between projects. So my idea was to take one of the old ideas that I had, and the idea was, why not doing some heavy metal? Train a deep neural network on heavy metal music and then have the neural network generate heavy metal music. So I started, and it took me 50 days implementing the entire idea, and implementation ended with my first album, Robot Uprising by Hexagon Machine, available on Spotify. So this was the end of the 50 days. The first day was nothing. So just darkness, like in Genesis, when nothing is there and let's create something. So I started with the implementation of that paper for a specific data set, which did not take that long. I think it took me 2 days to learn how Hugging Face works. Didn't know Hugging Face before, and also took me a half a day to write a rudimentary mapper for those pieces of music. Worked like a charm. Like after 2 days, I had the first neural network that composed chorales in the style of Johann Sebastian Bach and was already convincing. It's not that I spent a lot of time implementing and bug fixing and then training a lot of neural networks. It was one of the rare occasions where it just worked immediately. And I said, okay, fine. I'm quite happy about that. Why not making it a little bit more complicated, training this whole thing that I've now set up on heavy metal. So finding heavy metal music, pre-processing it the same way I pre-processed Johann Sebastian Bach music, and then train another neural network. And what happened is that I found on the internet some Russian server that has MIDI files, and I scraped it and I got roughly 7,000 MIDI files out of it. So in comparison to 400 or 500 songs, already different ballpark. It's not the biggest data set I trained on, I'll show you that later, but already quite big. So I had all the data, I did all the pre-processing, and I trained a couple of neural networks. This time I had to train a couple of neural networks because you should not pitch shift the drums, or else it will sound crazy. So after a couple of iterations and training for 4 days on 4 GPUs after 2 weeks, I trained 4 days, 4 GPUs. After the second week, I had my heavy metal model already. And then I had to implement a composer tool, so a tool where I can do some clicking, and then I got some music out of it. And then, most time I spent on actually composing and producing 12 songs and then uploading them. And also here, number 6, do the cover art, find the band name, find song names, also something. Cover art, I licensed a great piece of art from an artist. For the band name and for the song names, I talked to a transformer, GPT-J, I think, and we had a little man-machine brainstorming, and then it was all fixed. So after 50 days, starting from scratch, I had my first album online. And in these, in this whole time, I here the numbers 400 Bach chorales was the first neural network, and then I had on my hard drive 1,400 rock and heavy metal songs, and then I went to 7,000 heavy metal songs. And here is a little word cloud telling you the distribution of the different genres. So this is actually a neural network that is conditioned on genres. So I can ask it, please, neural network, be so kind, and compose some glam metal, which I actually never did, or symphonic metal, or black metal, stoner rock, power metal, metalcore, rap metal. And if you just tell it, well, give me some fresh metal, it gives you some fresh metal. And really good for creativity, because sometimes you're more in the doom metal mood, and then you ask it to create some doom metal, and then you get very happy about the results. So this is an overview of the distribution of different genres inside the 7,000 dataset. And this one we already had. Chorales? No, this one. This one is most interesting for us. This is, again, a piano roll. And if we look closely, you see again, well, there from left to right, there's the time. Top to bottom, bottom to top is the pitch, so frequency of the sound events. Again, 120 BPM, so 8 seconds for 4 bars. Each bar is 2 seconds. But this looks a little bit different from this here. Still a couple of voices, but the structure is different. So you see there are quite a lot of events, and sometimes you have multiple events at the same time, and multiple events at the same time for a voice. In a guitar, you have a power chord, for example, where you play a chord. But this is still the same piano roll representation. And this mapper that you see here for the Bach chorales just work like a charm with the same one. And if you look closely, I think orange, this is something that is not included in Bach. These are drums. So you have the kick drum, and you have the snare, and you have the hi-hats, and maybe crash cymbal here and there. Also works with the same notation. So you can just treat the drums as any other instrument where you have a pitch representation and a time representation. It works like a charm. Well, Hugging Face, all invited to have a look at that one. So music composed by AI. Let me show you something. It's also here in KI music. Hugging Face, Bass, GPT-2, it's the composer. And here, if you like, you can go wild at home. The composer, I think it would even work on your mobile hardware, so on your iPhone or Android phone. And this is something a little bit more extended. So I had the pleasure this year that NVIDIA saw what I was doing. I know a couple people from NVIDIA, NVIDIANs as they call themselves, and they asked me if I would consider using one of their servers for my trainings. And I said, well, okay, please. I'm always happy to train some neural networks on dedicated hardware with a couple of GPUs. And then they gave me access to a DGX2. A DGX2 is a server with 16 GPUs. 16. That's more than I ever worked with. So my trouble was, I had a lot of ideas, but it trained very quickly, and I wanted to keep it running. So after a couple of weeks, we had some neural network trained, and then they extended it. So I was busy for 3 months this year. I think a solid 3 months, keeping the server busy, training. And I started with rather small data sets. So at home, on your local computer, you can train on 400 and 500 songs. Maybe it takes a night to train that if you have a decent non-GPU laptop. For bigger data sets, you would go maybe to collaboratory. If it trains for 2-3 hours in collaboratory, it's still fine. But for bigger, really big data sets, you have to go to dedicated hardware. So the biggest networks that I trained them on 400,000 songs. So not 400, not 7,000, 400,000 songs. And this is the biggest dataset that is currently available. It's called the Meta-MIDI dataset, which is someone scraped the internet of all the MIDI files that they could find, and they deduplicated them. And it's 400,000 songs. If you think about this, and you can do the math maybe on your calculator, how long it would take to listen to 400,000 songs, definitely not something that you would love to do because it's way too much. And the beauty about that data set is that it includes a lot of different genres. So it's not only metal, it includes synth pop, it includes country. There's orchestral music in it. There's reggae in it. There's pure piano music in it. There are so many things in it. You train on it and you end up with a deep neural network that can do all those styles. And this here is an example. It's not trained on 400,000 songs, but on a good distribution of 15,000 songs. Still a lot. Not the biggest one that I've trained. This is a comparatively tiny dataset, 15,000. It's called the LUC dataset. LUC Clean is a small one. There's another dataset called LUC, just LUC. It has 175,000 MIDI files. Matter of scale. As I've told you before, deep neural network doesn't care as long as you have the same representation or a similar representation. I also played with the representation. So the only thing that if you can map one MIDI file to the text representation, you can map all the MIDI files to that text representation. And mapping all those MIDI files meant that there was one data set that I created. So from the MIDI files to the text files, and it took 30 hours on a computer with 96 CPUs. So it was just running. On this Mac, it would have taken 2 weeks to just do the data preprocessing. So you have hours, maybe days of data preprocessing, and then you take the data and you put it to a server where Hugging Face implementation is waiting for some training. You press play and tape, you monitor your losses via what they use, weights and biases. Then after a couple of hours, you have a deep neural network trained, or sometimes after 1.5 or 2 weeks. So on the big data set, when I trained it took, I think, 2 weeks until I find a good, a low loss. And this is the neural network that I'm currently working with my own compositions. So coming back, long story short, see, maybe I take another one. Instead. Yes, this one. There you go. Here's an overview of the datasets that I've worked with. Here, Johann Sebastian Bach chorales. So this is, comparison of size, small one. And this is the biggest one. Biggest one in representation, 230 gigabytes of text data, uncompressed text data. And the next one is smaller one, 130 gigabytes, so still quite a lot. And here, where is it? Here's the metal with 8 bars, and sometimes here is metal with 4 bars, and all the luck things available. So I had quite a lot of fun taking different subsets of MIDI files, mapping them to texts, and then training GPT-2 on that. And now, with GPT-2 available, I can conclude this part here. Unfortunately, you cannot hear this, but maybe it's something that you can see. Where you would go for a metal model, you will go for, let's say, hard rock, and you would say, let's generate the drums, and there you go. Takes a second. Now I have some drums, and when you have drums, why not? Let's add some guitar. So here comes the guitar, and metal is not complete if you don't have, where is it? The bass. Create another bass. So there you go. There's some music now generated by AI. I would love to play it, but this doesn't work with the Discord. It's no trouble at all. And this is actually how I would compose. I would start with something, and once I find something that I like, I would continue with that until I have enough material. Can also add some material more to the right. So adding more bars also works with the same neural network, although it has just been trained on 4 bars of music. And once it sounds nice here in this tool, I take it to Logic and then I turn it into an entire song. And just to finish this part of the story, for every song that I compose, I spend, let's say, 5 minutes with this tool until I have 30 or 40 bars of music. And then I continue the work in Logic. And usually for the first 3 albums that I did, it took me 4 hours for an entire song. Now it takes a little bit more because I also added vocals and add more detail to that. But I remember that this cuts the time for me in half. So if I start from scratch, and I'm perfectly capable of doing this in Logic, empty project, starting with something and then having a song up and running, usually 8 hours. Let's say without vocals and lyrics, but now it's just cut down to half, and I have never a writer's block. There's always some good music coming out of this tiny little piece of software, and it's never the case that I run out of ideas. And to finish this, it's the opposite. It's usually too many great ideas. Okay, thank you. So now we can talk about the questions if you like.
Thank you so much. This was really, really interesting. And I think we got quite a few questions in the chat, so I'm just going to start with the questions.
Perfect.
So the first one, I think, was relating to the slide where you showed the MIDI file of Bach, I think, and the text representation below. And the question is, how does POS encoding work here?
What kind of encoding?
It says how does... Yes. So how does positional encoding work here? Yes.
Positional encoding.
Positional, yes.
The positional encoding in the sense of what the transformer uses.
This is the question. So if the person can elaborate, but I think this is what they mean. Yes.
Yeah. Just straight to business, like in all those transformers. So P start is a token, track start is a token, instrument base is a token, bar start is a token. So everything separated by a space is a token. And it would get this sinusoidal positional encoding directly from the model. There are people, and I think I read a paper recently, that have more like a 3-dimensional positional encoding where you would have different musical events, tiny little atomic events, and you give them some certain position in positional encoding that would represent a little bit more. But here, positional encoding is just the position in the sequence, and everything else just comes from it naturally. So for this token, you don't know in which track it is, you don't know in which bar it is, but well, to the best of my knowledge here, it just works like a charm, that straight out of the box, and it's very versatile. So default, GPT-2, no special positional encoding. Even the tokenizer is a little bit less than GPT, it's just a white space tokenizer. With, vocabulary has 400 tokens, I think, just separate by white space, and then there you go. Great question.
Thanks, and thanks for the person who asked the question. The next question is there a way to represent music dynamics into the representation? A track could become quite long in sequence length. Would the maximum token length of the models determine the performance of the model more than we see in traditional NLP, as the attention mechanism might not take into account what's being played in the other parallel tracks?
Yeah. Okay, a couple of questions. Start at the end. The thing with the attention mechanism is I trained my models on just a sequence length of 2048, which means that I either have 4 bars of music and 12 tracks, or it's 8 bars of music and 6 tracks with 2048. Then it's usually exhausted on average. What I saw is that the attention mechanism, the power of attention mechanism, it works like a charm. So you could, it's all connected. As you've seen in my presentation when I composed, I never get anything out of the neural network that doesn't sound good. It's always harmonically sound. So you have a track and another track, and it's all based on top of each other. It's all harmonically sound. So this works like a charm. Yes, sequence length, definitely a bottleneck. There are other approaches, other representations where you encode way more music. So in a sense of more events, more bars, perfectly possible. I think there was recently a publication where someone used a linear transformer, because, problem with transformers is that it's both quadratic in time and space. So the bigger the sequence length, the more you are in hell. So they kind of went around this with linear transformers that also work with causal masks. So also something that people are working on. And there was another question. What was the first one? Can you help me? Are you mute?
I'm muted.
The first question in the beginning was, is there a way to represent music dynamics into the representation? I think this is the one.
Yeah. Music dynamics. It's no problem to add more tokens to that representation. So there's one token that is missing, it's the velocity. I don't include the velocity because velocity is something that I add the groove to the music is where I change the velocity. Also, it could be imaginable because it's included in the general MIDI standard to have those different control things where you do a pitch bending, for example, or change the instrument is also in there. And people are working now on an improved, or already did some great work in improved symbolic representation called MIDI 2, where you have even more events in it. But still, you would exhaust the sequence length. There's one thing, and it's also an answer to the question that I did not talk about. I just talked about symbolic music, where you generate note events. There's also other approaches, also based on transformers like Jukebox, where you would not generate the tokens representing pieces of music, notes, like sheet music, something that you read, but they would generate audio. Completely different thing, where I decided not to do it. And the reason for not going down this pure audio domain, where you can have everything in it, is that when you try Jukebox on a decent GPU, it still takes 4 hours to generate something. And it's just one generation. On the other hand side, this GPT-2 that I use, trained on 400,000 pieces of music with 4 or 8 bars, I click on my computer and it's immediately there. I immediately get the music because, well, it's not a really, really big one. It's just 6 layers, 8 attention heads. And it got some quite decent hardware acceleration recently because they published a PyTorch nightly build with, well, something that improves the CPU usage. And I'm crossing my fingers that they finally implement all the attention operations, because then it would be 4 times faster than it has right here. So I did the installation was 10 times faster. Now I'm waiting to it to be 50 times faster. Okay, great. Great questions.
Thanks. Great answers also. Thank you. The next question is the encoding you mentioned like tokenization step in text?
Well, yes. So in summary, the main idea is that you encode your music as a piece of text. If you work with this representation, there's something that you could even read. It's like reading sheet music. It's a little bit. It's not so easy to read, but reading music, reading tablatures, and so on and so forth. I mean, it's something that you have to learn, and then you like it. It's an acquired taste. Well, and that's the whole story. Once it's a text, it can be tokenized, and once it's tokenized, you can train a transformer on that.
Thank you. So I think I'm going to skip to. So, question to speaker: how is your experience with training coding phase models with M1 GPUs from Apple? Is it possible, or you use native PyTorch for trainings? And does the traditional scaling laws of LLMs also apply to music transformers?
Be patient. Be patient. I just bought this M1 Pro. Hugging Face GPT-2 comes in 2 flavors. One flavor is TensorFlow, which is, I think, hilariously accelerated now on the M1, and the also variant is the PyTorch variant. I did some experiments in those 50 days at the beginning, and turned out that the TensorFlow implementation of GPT-2 back then was not so stable, so I decided to go for the PyTorch implementation. You can train locally tiny little data sets with PyTorch GPT-2 on your M1, but it's more like a power horse for inference, so not for training. Still works. I think Johann Sebastian Bach takes 4 to 8 hours to train it. Something that I tried at the beginning to do some benchmarking, how fast it actually is. Again, it will be significantly faster once they finish this issue with the missing operations. So if you start Hugging Face, it will start PyTorch in a hardware accelerated mode, but it's not yet the GPU acceleration. So I remember before anything, I did a click and I had to wait for 3-4 seconds to get a result, and now it's just instantaneously. It will be even faster. So you have to wait a little, but training 400,000 songs on an M1 is still out of scope. And to conclude this, I'm waiting to get access to this Apple Studio, this Mac Max, I think. I think this should be comparable to an, how's it called, RTX 3090. So yes, decently 10,000 songs you can train overnight. 10,000. I hope once everything's accelerated. I'm waiting to do this benchmark. Okay, great question.
So I'm going to move to the next question. Are these models comparable with models such as TensorFlow Magenta, or is the approach completely different?
Comparable in quality, approach is different. So Magenta by Google, also a great project to get started with, to learn about what is possible, and also to learn that it might not be so possible to extend it with ideas that you have, because this is where it gets a little bit the customization with Magenta is not so, it's not the easiest thing. You spend quite some time implementing things. There are two things that are extremely relevant. It's all those RNNs that are available in Magenta, so LSTMs. I think most of the stuff they have there, or no, a good percentage of all the models they have there are LSTMs. The problem with that is that the quality of what LSTMs generate tends to degenerate the longer the sequences are. So they don't scale to that many sequences. There are models available that are multi-track in Magenta, but usually it's just 3 or 4 voices. It doesn't go to 12 voices, and well, it can even go higher in voices. With attention mechanism in GPT-2 just works like a charm, always consistent, no bad notes. With RNNs, LSTMs, it kind of degenerates. And there's also the music VAE by Magenta, which I really, really love, because it allows you to do latent space exploration of music and even interpolate between 2 pieces of music. It's very, very powerful, and it's something that I dearly miss. My transformer cannot do this, so I'm thinking about and working on ideas there where I could also have this kind of interpolation. But truth be told, in my own work, I didn't need that. So yes, long story short, Magenta, definitely great to have a look at, definitely great to do some work with. Those pre-trained checkpoints that they have, they are just marvelous. Just have to deploy them to production and then go wild. So definitely a good start, place to start. Great question.
Okay, thank you so much. I'm going to go back to a question that does the traditional scaling laws of LLMs also apply to music transformers?
I have no clue. Let me give you an anecdote. I started with this paper, MMM, and the paper said, now I repeat myself consciously, it's 6 layers, 6 decoders with 8 attention heads, 512 embedding size, 2048 sequence length. I was quite happy that it could compose Johann Sebastian Bach music. I was very surprised that it worked with 1,200 rock and roll and metal songs. I was really, really surprised that it even worked with 7,000 heavy metal songs. And after all those experiments that I finished before summer this year, the same neural network architecture, and I mean by the hyperparameters, not the pattern, but the 6 layers, it still worked with the 400,000 MIDI dataset with very, very good results. So what we have heard about GPT-3, that they could have trained the same model on way more data, but they didn't have more data. So it's still a little bit too big for the data itself. So it can throw more data on it. And I learned with the GPT-2 version that I used, no problem with a big data set. So I have the feeling that with the same architecture, I could train even more data and I would still get some really, really good results. But unfortunately, well, NLP is a couple of years ahead and doesn't have a certain problem that we music people have, because our bottleneck is the available data. And looks like that currently the available data is 400,000 MIDI files, which is nothing. So 200, 300 gigabytes of data. If you map it to text, nothing. It's with a lot of repetitions in it. If, on the other hand, we would finally have some successes of high quality transcription of any piece of music to high quality MIDI file, taking your entire Spotify collection and then mapping it to MIDI files, that would be a completely different thing. And I think people are already working on that. Great question.
So before I move to the other questions, I just have a question of my own regarding what you just said. Is it possible that there is a copyright issue with music if it generates something that already exists by accident?
Now it gets really complicated. First and foremost, I'm just a computer scientist, right? So when it comes to ethics and laws, I have no clue, and I'm very verbose about that. There are a couple of questions that now arise. When you think about Copilot, Codex, trained on source code that is available on GitHub publicly, but with licenses, turns out American law, the copyright law, does not apply to robots. Because how it's written, it only applies to humans. The lawyers say it's a very romantic law, because it just includes humans. So when an AI generates something, it's fair use. So can just do this. On the other hand side, in Germany, we have a completely different thing. We don't have copyright, we have Urheberrecht, which means that I created it. It's not the right to copy. It's a completely different thing. And here, it's not clear. It's very, very gray. So when you listen to music, sometimes you have quite a lot of sequences from other pieces of music. No one cares. Sometimes you have a tiny little piece of music, maybe 1 second, and then you end up in a court case for 20 years. I think it's Moses Pelham, the rapper, who took a sample from Kraftwerk, 1 second, and they are still in court because of that. So actually, well, I don't know. When I upload stuff to YouTube, something that I've generated, usually it never complains about any infringement. So it's new music, I would say. Sometimes when I listen to the music, I get some memories of other music. But well, that's the memory, because all or many pop songs, as an example, share the same chord progression. You hear the same chord progression, right? And if you think about how the Offspring has a song, how's it Self-Esteem, and there's Nirvana with Smells Like Teen Spirit, those are essentially the same chords, just arranged a little differently, 2 different songs, and no one got aware of that. And when it comes to the amount of copies that it generates, usually I would expect not that much, because we know from GPT-3 that it doesn't one-on-one replicate that much of the data set it trained on. So it happens maybe in 1 out of 1,000 generations, it does something. For me, in my entire work with that model, happened twice. So once there was Smells Like Teen Spirit by Nirvana with slightly different drum pattern, and then something that sounded like Das Modell von Rammstein, this cover version of Kraftwerk. I also expect that it is going to raise a couple of eyebrows and that we are going to have quite a lot of discussions about that. Great question.
Thank you. The next question we have in line is, can you show us some examples? Can you save it and post it here? I'm very eager to listen to it. And I think an adjacent question would be, if what you just showed us, can we actually play around with it?
Yes. When you go to ki-musik.de, you get access to at least 2 spaces on Hugging Face where you can compose music. And the one that I showed you last, the composer, you can even download the music and publish it anywhere else. You can click a couple of things and generate something. You can be very happy with that. The tool that I've created for my own music, this is not open. This is just for me, and I'm thinking about working towards turning this into some kind of product. Like first, I have to upload the checkpoints and so forth. So it's quite some work. It's still on my desk. So yes, there are a couple of models available, Hugging Face, to play with. If you are curious about listening to the music that has been generated by man and machine, It's not that you click and you get an entire song. It's that you always interact in a dialogue with the music. My band is called Hexagon Machine. You'll find it on Spotify and all the other streaming platforms. And if you just quickly search on YouTube, I have a channel there where I uploaded quite a lot of things and talked about a lot of things, and there are demos and samples available there. Great, thank you.
So I'm going to move on. There is a question about how long it takes to generate a composition, and there is already an answer in chat. The inference should depend on the machine you're using. So yes.
Yeah. I remember that on average it was 4 seconds for 4 voices, 4 bars before the PyTorch nightly build, and then it went down to 0.3 seconds for the same amount of nodes. So it's just instantaneous. And again, with hopefully one of the future nightly builds and then stable versions going to be even faster, because it's still not using the entire CPU.
So do we have time for 1 or 2 more questions maybe before we wrap it up? Thank you.
Yeah, fine with me.
So I think I'm going to go to, is there any conditioning going on between the different instruments you showed in the last tool? It is, does the backtrack know about the drum track, or are they generated completely independently from each other?
They know of each other. So the whole composition starts with P start, and then it adds, if I start with drums, it adds drums to it, and then it adds the guitar to it, and so on and so forth. So it's conditioned on itself. So it's one long sequence that I continue by clicking on the whole thing. So this is why it's so harmonically sound. I also have a deep neural network that is trained on more conditions. So when you take a look at a piece of music, you can analyze it harmonically and find out the underlying chord structure, like C, B, C, E, G, F, and those fancy things that you have everywhere. And I have a model where you start with just symbols of the chord progression, and it would compose something following that chord progression. It's like prompt engineering. You just have to come up with the right prompt. But still, it's one long sequence, and the sequence can be quite long. Yeah. Great.
There's another question from Michelle. Is there already a pre-trained model available?
Yes, the Johann Sebastian Bach model is available on Hugging Face.
Yes.
And the 15,000 songs luck model is available in this space where you can just play it.
So I don't see any more questions in chat. So if anyone has any more pressing questions, they can ask them now. But if there are no more questions, I would like to first say that I think it's going to be very exciting in the coming months, even, or years, because with the developing technology and when music generation with NLP models catches up to classical NLP models, it's going to be fascinating when we don't just have like 400,000 pieces to train on. So I think it's going to be really interesting to see what happens. And yes, it was a really fascinating talk, because you use NLP models to generate music, but you can also, there's some stuff like that, because music is a language. So there are stuff emerging from music production that you can track back to language. So I think it's really, really fascinating field. So I would like to thank you for the great talk. And I just had a funny little question in chat that just came up. So I would like to ask it. Takeo just asked, do you think musicians will be angry at your product?
Some, but just a few. just a few. The good thing is, again, not replacing musicians, giving creative people better tools to do something, right? It's about increasing, augmenting human productivity and creativity, not replacing the human at all. So I can think about this whole harmony things and like which chord progression to use, and this is a sad one, this is a positive one, and then do this clicking of the notes and play something on my instruments. But these deep neural networks, they accelerate that. But I'm still in charge in this very nice setup of having a nice dialogue with, well, quite a lot of musicians, because at the end of the day, 400,000 songs. I mean, how many musicians were involved? It's a fascinating time to be alive.
Yeah, this is what really makes an impression that you don't actually take the human out of the loop. So it's constantly there, like in your work. It's continuously there when it's working with the AI.
Spirit is missing, I tell you. I have implementations here on my hard drive, and there's one implementation where you would start a composition and let the AI just continue bar by bar by bar by bar by bar. It's meandering. It's always harmonically sound. All the transitions are just perfect. All the chords are perfect, but it doesn't tell a story. Just going left, right, not really a story. So you don't have an intro or verse and then chorus, pre-chorus, maybe bridge, coming back to verse, and so on and so forth. And this is something where I still have a lot of responsibility, making sure that there's a chorus, that's a verse, that you have more traditional song structures. Getting there, Magenta, they have published something, it's a diffusion model. So we are very happy about diffusion models like DALL-E 2 for image generation that would generate something with longer structure. Yeah, also available by those great people from Magenta.
Once again, thank you for the very interesting and fascinating talk. I really enjoyed it. Thank you for your patience with the slight technical issue in the beginning. Thank you so much. And thank you everybody for joining us. And yes, I really hope to speak to you again sometimes. Thank you.
Yeah, thanks again for the kind invitation, and thanks for this opportunity to talk a little bit about things that I'm doing. So it's quite my passion in doing something and then talking about that was awesome with you. Thank you very much.
Thanks. Thank you.